successor is in it. Well, those two properties precisely define what it means to be an inductive set. But omega has been constructed as the smallest possible inductive set. In other words, it's a subset of every other inductive set. And so you just automatically get that this set Q just is omega. Because Q is a subset of omega, and now omega is a subset of every inductive set. So if Q is inductive, then omega is a subset of Q, and Q is a subset of omega, so Q equals omega. Does anyone know what I'm talking about? It's really hard. Some people are somewhat following. Good. Woo! What else? What is this? Oh, this is the last axiom of piano arithmetic, which says that the successor function is 1-to-1. And it just works. It works, I promise. Okay. One by one, man. We're rebuilding all of math from scratch. What else can you do in ZFC? Just anything you want. For example, let's go back to the piano arithmetic lecture in early December, and let's see how I can carry this stuff out in ZFC. Oh, I can define addition recursively in terms of the successor function. Let 0 plus x be x, and let the successor of a number plus x be the successor of n plus x. That's the recursive definition of addition within piano arithmetic. But of course, our successor function has been defined in terms of sets, and so in fact, I've defined addition in terms of sets. I can define multiplication in terms of sets. I can define, I guess this is exponentiation that she's defining. No, what is that? 0 is 1, yeah. And so, in other words, we've recovered all of arithmetic. All right, good. Another axiom. This one is notoriously difficult to understand. It is a fancy one. It is called the axiom of replacement. I have only a sketchy understanding of it myself. Roughly speaking, if you have some set, ABC, and you have some function, then this axiom gives you the power to construct the set of all the sort of images of that function applied to some set that you've already constructed. So the very loose understanding of this is, given some set ABC and given some function f, then you can construct a set f of a, f of b, f of c. And this is needed for some like very technical parts of set theory. I hesitate to even necessarily read aloud this or try to parse this first order logic phrase. Let's not do it. Zermelo, this is one of Frankel's key contributions, the axiom of replacement. And Zermelo by this point was like checked out. He was like, I don't know what's going on anymore. I lost control of my set theory. He did sort of notoriously like late in his career when he was still like not that old yet. Just had no idea what the hell was going on anymore, and people just passed him by. He's kind of famous for speaking publicly and just being wrong over and over and over again late in his career. Why is the axiom of replacement important? For us, it's probably not important. Zermelo does. I'm not sure if Frankel does. I'm not sure if Frankel does or other people did this, but you can prove that the axiom of replacement is indeed independent of other axioms by creating a model of ZFC, whatever that means, in which the axiom of replacement is false. This is a direct quote from this set theory textbook that we built this whole presentation out of. And the comment is, the axiom of replacement is unnecessary for most theorems in ordinary mathematics. In other words, you could probably go your whole life and not need the axiom of replacement. But what do you need it for? To construct some obscure sets, such as omega, omega plus 1, omega plus 2. Suppose that you really needed that set for some kind of reason in your life. Well, you can't get it out of axioms 1 through 7. You need the axiom of replacement. Okay, yo.
The way you're selling this, it makes me think that like Zermelo was right and we really don't actually need it.
We need it for sets like this.
Yeah,
do we need sets like that? I don't need that set. Okay. Others might need that set. Okay. I'm glad you're pushing back on this because do you see it's like a little bit of a game, right? It's like there's like a game, right? Here is the like moat of death, and in here is Russell's paradox, right? And if you go too far and you give yourself too much power, you fall in the fiery moat and die. Let's see how many metaphors I can put all together in one. Okay, so now, but you want power, right? So the more axioms you give yourself, the more power you have. But you gotta be careful not to give yourself too much power. Because if you give yourself too much power, you will fall into contradiction. And so the axiom of replacement gives you more power, but maybe just a tiny bit more power, such that you can make some obscure sets that you need for some very, very technical purposes. The axiom seems pretty harmless, so we'll just take it. Yes?
So like, I think it's saying you can like apply a function to every element in the set.
That's all it is, yep.
But like, that seems useful. I have
Yeah.
a set, I want to apply a function to
Yeah,
every
it does
set.
seem useful to me, yeah. Yeah.
Well,
Good, good. Woo. All right, the last axiom is the axiom of choice. Depending on your level of understanding of the axiom of choice, then there's nothing more to say. Great. We might be ending early. Woo! Conclude. Is this the last slide? Yeah. Okay, conclusion. We did it. Kind of. We have taken set theory, indispensable for mathematics, and we have applied to it the axiomatic method, the thing that's been the organizing principle of mathematics going all the way back to Euclid. If you have some field and you want to truly understand that field, you axiomatize it. Well, to their discredit, no one felt pressure to axiomatize set theory prior to Russell's paradox. They preferred to leave it as just some vague guiding principles that could not possibly go wrong. It was Russell's paradox itself which forced people to go back and to rescue set theory, and they did. And so ZFC, basically, when I'm saying now, I mean 2020. Loosely speaking, ZFC is, currently in 2020, the foundation for all of mathematics. By that, I mean, it is a set of axioms through which one may construct sets, not sets, of course, but not just sets, things which you could charitably call natural numbers. And through the process of going backwards through the 19th century, you can construct out of those natural numbers, rational numbers. You can construct out of those rational numbers, real numbers. You can construct functions by constructing ordered pairs, etc. And so the entire project to build all of mathematics on a firm foundation, using one single language, has kind of been achieved. We can do all of piano arithmetic within ZFC, and basically every single set that we could ever possibly need in mathematics, you can build out of ZFC. Okay, so take any page out of any mathematics textbook, turn some, just pick a page in your multivar textbook, page 611. Open it up, and if you really, really wanted to, you don't want to, you could continue rewriting that page in lower and lower level translations until you eventually got down to bare statements about sets of real numbers. Don't stop there. Go to Dedekind cuts. Go to ordered pairs of naturals. Write out every ordered pair as a set. What you will eventually have, that one page, is probably like a 500-page long sentence in ZFC. Okay? ZFC serves as the universal language of mathematics. Any branch of mathematics can, in principle, be written in ZFC. All right, so what's the catch? Are we done? Did we win? Did we fix everything? Yeah.
Do there exist another set of valid axioms for set theory?
Wait, hold on. Before you go proposing other axioms, there's just one glaring. There's just one glaring problem. What did we set out to do 25 hours ago? What was advertised, the whole point of ZFC? What was the whole point? Fixing Russell's paradox. In other words, avoiding contradiction. Naive set theory is inconsistent. So ZFC is, I don't know. Is it inconsistent? Well, no inconsistencies have ever been found.
I mean,
Okay, well, we don't. No, there have been no inconsistencies found in ZFC. That's a fact. But really, you shouldn't actually be confident about the success of the program to establish the foundations of mathematics with new set theory axioms until you have proven, actually proven, that these axioms do not lead to a contradiction.
But wait.
Okay, but now we go back to a comment that was supposedly made during the Hilbert presentation, or I hope it was. How are we going to prove that the axioms of ZFC are consistent?
Model.
We have to make a model. But a model out of what? We've run out of stuff, man. Sets are already the most simple, fundamental, basic mathematical objects that exist. There is no other background theory to construct a model out of. I don't even know what a model of ZFC would even look like. Do you? How am I going to show? We're not really done until we can show that these axioms of ZFC do not lead to a contradiction. If they do lead to a contradiction, then they're garbage. If hiding inside ZFC is like a no dogs in the pool, dogs must be in the pool contradiction, then this entire thing is just worthless. And until we show that these axioms don't lead to a contradiction, we haven't really accomplished anything at all. You can hope that they don't lead to a contradiction, but until you know that they don't, you're not done. And I don't know how to do that. That sounds really hard. Okay, good. To be continued tomorrow, cliffhanger, by period 7.